Welcome to the 8th lecture in Applied Math. The topics that we will explore in this lecture include matrix products and linear combinations, and an introduction to inverses. Okay, so we'll start this lecture by looking at the exercises from the previous lecture. And in the first exercise, we have the equation, the row vector x, y, times the 2 by 2 matrix with columns 3, 2, negative 2, 5, times the column vector xy is equal to 30. Now, because matrix multiplication is associative, we can either multiply the last two matrices and then pre-multiply the result by the first, or we can multiply the first two matrices and then post-multiply the result by the third. In either case, we have the degenerate 1 by 1 matrix, which is algebraically equivalent to a scalar. So let's choose to group the last two matrices. So we have the row vector x, y times the 2 by 1 column vector 3x minus 2y, 2x plus 5y is equal to 30. So we have x times the quantity, 3x minus 2y, plus y times the quantity, 2x plus 5y is equal to 30, or 3x squared minus 2xy plus 2xy plus 5y squared is equal to 30. So we have 3x squared plus 5y squared is equal to 30. Dividing through the equation by 30, we have x squared divided by 10 plus y squared divided by 6 is equal to 1. This is the ellipse centered at the origin. With major axis on the x-axis and endpoints square root of 10, 0, negative square root of 10, 0, and semi-major axis on the y-axis with endpoints 0, square root of 6, and 0, negative square root of 6. And in the second exercise, we have a 2 by 2 matrix A with columns 1, 0, 2, 1. And we need to find a 2 by 2 matrix B that is not the zero matrix and is not the identity matrix, such that A times B is equal to B times A. So we'll set up the equation, the matrix A times the 2 by 2 matrix with rows A, B, C, D is equal to the 2 by 2 matrix A, B, C, D times the matrix A. So on the left-hand side, we have the 2 by 2 matrix with columns A plus 2C and C, and B plus 2 times D and D. And this is equal to the 2 by 2 matrix with columns A, C, 2A plus B, and 2C plus D. Now, since these matrices are equal, the corresponding entries are equal. So we have A plus 2 times C is equal to A, in which case 2 times C is 0, and so C is 0. We also have B plus 2 times D is equal to 2 times A plus B. So we have 2 times A is equal to 2 times D, or A is equal to D. So let B be the 2 by 2 matrix with columns A0 be A, where the entry B is not equal to 0 whenever the entry A is 0 or the entry A is 1. Then A times the matrix B is equal to B times the matrix A, where the matrix B is not the 0 matrix and the matrix B is not the identity matrix. So there are infinitely many matrices B such that A times B is equal to B times A. Now notice that if A times B is equal to B times A, then A and B are both square matrices of the same order n. So new definition, let A sub 1, A sub 2, and so on through A sub r be m by n matrices with real entries, and let C sub 1, C sub 2, and so on through C sub r be scalars. An expression of the form C sub 1 times A sub 1 plus C sub 2 times A sub 2 plus and so on through C sub r times A sub r is called a linear combination of the matrices A sub 1 through A sub r with coefficients C sub 1 through C sub r. So next we'll prove a theorem. Let A be an m by n matrix with real entries, and let X be an n by 1 matrix with real entries. That is, X is a column vector, and in general I will denote a vector with a lowercase letter and an arrow above it. Then the product, A times X, which is an m by 1 column vector, can be expressed as a linear combination of the column vectors of the matrix A with coefficients the entries of the n by 1 column vector X. So proof. Let A be an m by n matrix with real entries, and let x be the column vector with entries x sub 1 through x sub n. Then A times x is the m by 1 column vector with first row a sub 1 1 times x sub 1 plus a sub 1 2 times x sub 2 and so on through a sub 1 n times x sub n. Second row a sub 2 1 times x sub 1 plus a sub 2 2 times x sub 2 and so on through a sub 2n times x sub n and so on, so that the mth row is a sub m1 times x sub 1 plus a sub m2 times x sub 2 and so on through a sub mn times x sub n. This is the sum of column vectors a sub 1 1 times x sub 1, a sub 2 1 times x sub 1 through a sub m1 times x sub 1 plus a sub 1 2 times x sub 2, a sub 2 2 times x sub 2 through a sub m2 times x sub 2 and so on through a sub 1n times x sub n times a sub 2n times x sub n through a sub mn times x sub n. This is x sub 1 times the column vector a sub 1 1, a sub 2 1 through a sub m1 plus x sub 2 times the column vector a sub 1 2, a sub 2 2 through a sub m2 and so on through x sub n times the column vector a sub 1n, a sub 2n through a sub mn. And so the product is a linear combination of the row vectors of A with coefficients, the entries of the column vector x. So given an equation of the form A times x is equal to B, the column vector B is a linear combination of the column vectors of A with coefficients the entries of the column vector x. So let A be an M by P matrix with row entries, and let B be a P by N matrix with row entries. In the last lecture, we looked at multiplication entry-wise. That is, the entries of the product A times B are each products of rows of A times columns of B. This time we will look at multiplication entire rows or entire columns at a time. So since the matrix B has n columns, we can think of it as a row vector containing n column vectors where the jth column vector has entries B1j, B2j through BPJ for j ranging from 1 to n. So the product A times B, the product of the matrix A, times the row vector of column vectors B1 through B sub n, which is the row vector of column vectors A times B sub 1, A times B sub 2, through A times B sub n. That is, the jth column vector of the product A times B is the matrix A times the jth column vector of B. Similarly, since the matrix A has m rows, we can think of it as a column vector containing m row vectors where the ith row vector is the row vector with entries a sub I1, a sub I2 through a sub IP for I ranging from 1 to m. And so the product A times B is the product of the column vector of row vectors A1 through AM times the matrix B, which is the column vector of row vectors A sub 1 times B, A sub 2 times B, through A sub M times B. That is, the ith row of the product A times B, ith row vector of the product A times B, is the ith row vector of A times the matrix B.